Hello guys, how are you?
I'm good, yeah.
Good.
Okay, so let's start. So we have, a big lecture today. So this will be actually two lectures. The lecture of Tuesday and, this today's lecture as well, combined. Okay, so you guys can see my screen? Or no, I think no.
No, we do not see your screen.
Okay, now,
Yeah, we see it now.
okay. Okay, so today we're gonna explore a module inside our microcontroller of our robot kit, okay, called UART device. So this device is basically used by the microcontroller to communicate to other modules or other, to the external world, we can say, okay? So for example, if you wanna send data from your computer to your the launch pad or the robot, okay, you need some sort of communication, okay, communication protocol. In other cases, maybe this microcontroller is communicating to some sensor, like for example a GPS sensor module. So this GPS sensor module or receiver will continuously send data, which is updated information of the location of the robot, okay. And you need also some sort of communication to understand, what's coming in from that GPS receiver, okay. Maybe also this microcontroller is communicating with another microcontroller, okay. So there are many, many applications for the UART. One simple application is to debug your robot, okay. So the robot will send you some information about what's going on, okay, based of course on your configuration, what kind of data you want to read, and based on that data that you read, you know what's happening with your robot kit, okay, if it's behaving right or wrong. So there are many, applications for on many applications why you need you need to communicate with your robot, okay. And one piece of hardware that is used to make a communication is called UART. There are also other hardware modules which use different hardware communication protocol also inside our robot, but we're gonna concentrate on the UART because it's more famous. So we have two types of communication. We have serial communication and we have parallel communication, okay. So basically in parallel communication, you have two microcontrollers, for example, or two devices, two computers even, okay, and you have many lines to transfer the data. So for example, here you can transfer 4 bits at the same time, okay. Guys, by the way, this theory part will be graded, so I published a quiz, okay. So this lecture is not only a code, and you must also understand the theory behind the UART communication, because it's useful not only for our robot but also for other robots or kits. Another way of communication is using serial ports. So in serial we just send bit by bit. So I just forgot to put that. So in serial we just send bit by bit serially behind each other. Yeah. Okay, that's fine. I can update it later. So you can just imagine that bit 0 is sent, then bit 1, then bit 2, then bit 3. Okay, so you just use one wire here and you send these bits serially, bit by bit. Of course, you will say that parallel is much more convenient and faster than serial, and that's right. but this was for old computers. Okay, yes, it's so fast, but first it needs more wires. Okay, and basically more hardware inside the transmitter and the receiver to handle, these, or this concurrent sending of bits. Okay, and also there is a problem called the crosstalk, and this crosstalk problems usually limit the maximum frequency that you can reach, how many bits you can transfer per cycle. With modern computers and microcontrollers, the frequency is really high, and this serial communication, has no crosstalk problem, and you can reach, satisfiable speeds with less amount of hardware, just like parallel. So nowadays, most of the communication protocols are based on serial protocol. For example, USB. Okay, USB is a kind of serial protocol, different from UART, by the way. Okay. So basically, our microcontroller, okay, implement a serial way of communication using UART, because you can implement serial communication using also other modules rather than UART. Okay, but ours is using UART. Another definition that we must understand also, which is synchronous versus asynchronous communication. Okay, in synchronous communication, the sender and the receiver, must be clocked at exactly the same clock cycle, which is really hard to achieve and not generic. So whenever you buy some module, some piece of hardware, and you wanna communicate with another hardware, you must buy, a matched hardware, a matched module that has exactly the same frequency, which is really hard. Okay, and makes your design limited. For that reason, people come up with another way of communication, which is asynchronous communication, not asynchronous teaching. Okay, so in asynchronous communication, you have a transmitter and receiver. Generally, they are using two different clocks. Okay, but they will agree upon the same transmission and receiving, rate. So the transmission part and the receiver part, I mean the hardware for the transmission and the hardware for the receiver, okay, are both at the same clock, but this may be different from the main clock of each module. Okay. And whenever there is a communication, we need some sort of start, like for example, how to start a communication, and how to end it. So we need some sort of protocol, and it tends to be very easy to do. Okay, so again, most of nowadays, communication protocols between hardware modules is asynchronous as well, serial and asynchronous. Okay. So as I said, most of microcontrollers nowadays use asynchronous serial communication protocols. UART is one of these modules, or one of these hardware modules that implement asynchronous serial communication. Okay, and our MSP432 adopts UART devices. It also adopts other asynchronous serial protocols, but the most famous is UART. Okay, and the most easy to use as well. Okay, UART as a in specific, it has its own features. Okay, this hardware that implements asynchronous serial protocol has its own features. First of all, data is transferred byte by byte. Okay, oops, sorry. So data is transferred between a transmitter to a receiver byte by byte. Okay, so if you have a large chunk of data, okay, you must divide them into bytes. Then you send byte by byte. Of course, each byte is 8 bits. I don't need to say this. It's obvious that byte is equal to 8 bits. Now, the transmitter need to tell the receiver when it's gonna start a communication. So we usually put what's called the start bit and end bit, okay, enclosing these 8 bits. So I will send a byte now, for example. So I will send first a bit. This is called the start bit. So whenever the receiver receives this start bit, he knows that there is a communication going on. So he will be ready to receive my data. And at the end, after the 8th bit, after, you know, it's 1 byte, after the 8th bit, I will add another bit called end bit. And whenever the receiver sees this end bit, he will know that the communication is ended and he received all the bits needed. Okay. This communication is really simple because it needs only 2 wires. Of course, 1 wire for the bits and the other is just the ground. So, you know, technically it's just 1 wire, okay, because the ground is just points, okay. But if you have duplex communication, I mean, both module can transmit and receive, then you need 2 wires, one from this part to this part, and one from this part to this part, okay. So you now need 3 wires, or practically speaking, 2 wires plus a ground, okay. Finally, UART uses what's called the TTL logic, and let's go into details of this TTL logic. TTL logic means I will use high as, you know, 5 volt or 3.3 volt, and low as 0. So whenever I will send 1, I will send logic high, which is 5 or 3.3, and whenever I want to send 0, I will send 0 volt. There are other type of logics that use positive voltage and negative voltage, and they didn't use even 0 at all. Okay, so it's important to know what TTL means. In TTL as well, we send 1 byte at a time. Okay, and we call this a frame. We send the least significant bit first. So if you have a byte, you send it from the least significant bit, not from the most significant bit. Okay. The start bit, we said that we need a start bit to start the communication and an end bit to, or, you know, stop bit to end the communication. So the start bit is always 0, always 0, and the end bit is always 1. And when there is no communication, I will put the line, the wire, into high voltage. So whenever I have a high voltage, you know, all the time, that means the line is idle. There is no transmission is going on at that time. And whenever I will start the communication, I will send 0. Look, so here's the line was idle. Then I sent a 0. I mean the transmitter sent a 0. So the receiver, when it sees this transition from high to low, he knows that there is an incoming byte now. Okay. For example, if you want to send this byte here, 11010010, remember we send first the least significant bit toward the most significant bit, then the stop bit. So we send, after the start bit, we send 1, the least significant bit, then 1, then 0, then 1, then 0, 0, 0, 0, then 1, then 0. Okay, then the stop bit, which is always 1. So the stop bit is always 1. Okay. Again, this is we started by the least significant bit and we ended by the most significant bit. Okay. Usually, when we measure the speed of a communication between a transmitter and a receiver, we measure it in something called the baud rate. And remember, in general, the transmitter and the receiver may be working at completely different clock cycles. For example, today we're gonna communicate between the PC, your PC, and the kit, the robot kit. Remember, your PC processor, you know, maybe working at 2 gigahertz or something. Most of current nowadays processors are, you know, very fast, 2 gigas or 3 gigas. But our guy here, you know, maximum frequency is 48 megahertz, which is, you know, 0.048 gigahertz. Okay, it's very small. So, however, they have different clock cycles, but they agree on the same baud rate or the data rate that that the robot can send using this rate to BC, or BC send it to robot using the same data rate. Okay. Also, they have different clock frequency. So the baud rate is actually the number or the total number of bits transmitted per second. Okay. So if you want to know the time of one bit, okay, you just divide by one. You just divide by this baud rate. So 1 over the baud rate will give you the time required for each bit. So for example, if the baud rate is 1000 bits per second, then each bit takes 1 over 1000 second, which is 1 millisecond. Okay. Again, as I said, both the transmitter and the receiver must agree on the same baud rate, although they may be working at different clock frequencies. Like in our case today, the processor the microcontroller is working at 3 megahertz and or 12 megahertz. We will set it to 12, and your computer is in gigas. Okay, so huge difference. If we want to measure the number of bytes, okay, per second, we divide the baud rate, which is the bit rate. Now we want the byte rate, okay? We divide the baud rate, which is the bits per second, by 10, not by 8. Although one byte is 10 bits, but it's 10 bits of data. But remember, we add a stop bit and a start bit. So to send 8 bits, we actually send 8 bits of data. We actually send 10 bits because we send also start and stop bit. Okay. So whenever you want to know how many bytes are sent per second, not bits per second, you divide the baud rate by 10. Typical baud rates, is 9600. These are, standard numbers. You cannot just imagine or choose any number. So you must conform to the standard. So there are many, standard baud rates. Okay, and you must choose one of those. You cannot just, choose to work with another baud rate. You will have error in transmission or receiving. One may say it's good to use high baud rate because high baud rate means high bit rate. So we have faster communication. That's right. But at the same time, we often see at high baud rates, although it's faster, we often see some transmission errors. Okay, so it's not always good, especially with simple microcontrollers like our microcontroller. You may have some problems in the receiver of this microcontroller at high frequencies or high baud rates. Okay, so let's examine. So high baud rates are good, are faster, but low baud rates are more reliable. So you will have no mistakes, we can say, or less mistakes. Okay, and of course, if you have a mistake, you must, if you choose some baud rate which is high and you got some transmission errors, you must go to a lower baud rate to avoid these errors. So let's have a quiz for 1 minute. Okay, so how many bytes transmitted if you have a baud rate of 9600 bits per second, which is the baud rate? How many bytes transmitted per second? Can anyone,
960.
That's right, 960, because we should divide by 10. That's right, not 8. Okay, how long it takes to transmit 1 bit? You need a calculator for this. Any volunteer? We have one here. Yeah. Thank you, Clark. So Clark said it should be 1 over 9600. It will be 104 microseconds. Okay, that's good. So let's say, let's now answer the question why low baud rates are, more reliable, or the probability of having errors are less. Okay, so let's assume that you have at the receiver the clock, the receiving clock, which is different from the clock that the module is working. So maybe the receiver is a microcontroller that is working at 48 megahertz, but the receiving clock for the UART module itself have a different clock frequency. Okay, let's say it was off by 4 micros, or skewed. Guys, clock skew means some delay each clock cycle. It's off by 4 microseconds. Okay, and let's say this is and we are working at 9600 baud rate. So the time for each bit is 1 over 9600, which is 104 microseconds. Good. Usually when we read a bit, we clock at the center of the bit. So the blue locations here are the correct, or what should be the clock edges to read the bits. So we should have a clock edge at the center of this bit. We should have to read 0, which is the start bit. We should have another clock edge at the center of this bit to read 1. We need also a clock edge at the center of this bit to read another 1. Again, the clock edge should be here also at the center to read 0, and so on, to read the correct byte, which is 0, 1, 1, 0, 1, 0, 0, 1, 0. Okay, now let's see what is this 4 microsecond will do with our measurement. So when I say there is a 4 microsecond clock skew, or the receiving clock is off by 4 microseconds, so each clock cycle there will be extra delay of 4 microseconds. So let's assume that the first bit, the receiving clock, which is now the wrong one, or the bad one, is the red arrows. Okay, so at the start bit, the clock was at the center, so we read 0. That's good. If we assume that this time is 0, so the center here will be at 52.1, which is 104.2 over 2, which is 52.1. Good. So the second center should be at time equal to 52.1 plus 104.2, because one bit is 104.2 microseconds. But for our practical clock now, which is the red one, there will be 4 microseconds extra. So it will be 52.1 plus 104.2 plus 4 microseconds. So it would be 170.3. It's still within the bit, so no problem. We will read 1. Good. So how about this one, the third bit? The right clock edge should be at 166.3 plus 104.2, so it should be 270.5. The bad one would be 170.3 plus the time of one bit, which is 104.2 plus the clock skew, which is another 4 microseconds. So it would be 278.5. Still, we are within the bit, so we will read 1. And we will continue the same. As you see here, as we go forward, there is more divergence. There is more, we are going more away from the right location or the center. Okay. Luckily, by the end or the stop bit, okay, we are getting here the highest, the highest clock skew. The right clock edge should be at 989.9 microsecond. The bad one is at 1025.9 microsecond. It's still within the same duration of the stop bit. So we will read at 9600 baud rate, we will read correctly the byte. Okay, and there will be no problem. But if you choose to work at a higher baud rate with the same clock skew that you will have problems. Let's see how. So at that baud rate, the time of each bit is 1/38,600, which is 26 microseconds. So again, for the same byte, but now the time of each bit is less. So at the center here, if we start at t = 0 at that point, so both at t = 13 microseconds. That's good. Then after one clock cycle, the correct edge should be at 13 plus 26, which is 39. The bad one will be at 13 plus 26 plus 4, which is 43. It's still within the perimeter. This one, the correct is at 65. The bad one is at 73. We're still within the perimeter. Look at this one. This one, the correct is 91. The bad is 103. This is, 2 microseconds away from the edge. And in the fourth here, we start to see problems, until at the last bit, which is the stop bit, the correct is at 247, and the bad is away from the stop bit. It's at 283. Remember, the last time here is 260. So this is bigger than 260. It's at 283 microseconds. So we will read different incorrect data. Okay, and at that time you should, of course, reduce your baud rate. I see this myself. Okay, in some some processors, if you choose high baud rate, you will have problems. Good. So there are actually, as we said, there are UART module inside our microcontroller in MSP432. Also, it's not just one. You have 4 UARTs: UART 0, UART 1, UART 2, UART 3, just like the timer. So you have 4 timers as well. You have timer A0, timer A1, timer A2, timer A3. So you have 4 timers. I'm sorry, you have 4 UARTs: UART 0 to UART 3. Okay. And all these UARTs are full duplex communication. I mean, they can transmit and receive at the same time. So let me check this. Okay. You have, so we need 2 pins, okay, from the microcontroller to connect or to communicate to each one of these UARTs. So for example, UART 0 uses pin B1.2 as receiving bit and pin B1.3 as a transmission bit. So if it want to send something, it will send it using this pin 1.3. And if you want to send something to UART 0 inside your microcontroller, you should use pin B1.2. Okay, same for UART 1, but different pins. B2.2 for receiving, pin 2.3 for transmission, and so on for the other UARTs. And these 4 UARTs can work independently, concurrently at the same time. So you can basically, in principle, you can communicate to 4 sensors, for stuff at the same time. For example, you can communicate to your PC, your GPS module, if you have another microcontroller, okay, another sensor, a 4th sensor at the same time. So let's check how UART transmit operation is taking place. This is very important because the programming itself, will be dependent on this understanding. You cannot program UART without understanding this part. This is very specific to our microcontroller. Okay. So to transmit, the transmit operation of any UART inside your microcontroller. Also here we will use UART 0 as example, but the same for UART 1, UART 2, and UART 3. Again, each hardware module inside your microcontroller use some sort of registers, okay, to perform its function, either to control it or to receive or transmit, something like this. Okay, so basically, step one is to write, the data that you want to send to what's called the transmission register. So each UART has a buffer. Transmission buffer. Each UART, UART 0, UART 1, UART 2, UART 3, has its own transmission buffer, TX buffer. And again, if you have a big chunk of data, you should them 8 bits or byte by byte. Okay, so for example, for one of these 8 bits, the first step is to write these 8 bits to what's called the transmission buffer. So for example, for UART 0, this transmission buffer is called UCA0 TX buffer. Okay, so you write this, and there is a flag here called TXIFG flag. And whenever you have a full transmission buffer, this flag will be 0. And why this is important? Because if you check this flag or this bit in another register called UCA0 IF interrupt flag register bit or interrupt flag register, okay? Whenever you check this bit and you find it 0, that means that your transmission buffer still have data that is not transmitted yet. Okay. The second step is to write this data, and this is not your action here is the thing that the programmer do is to write to this buffer. The rest is what the microcontroller will do for you. Okay. So the microcontroller, whenever it sees data here, it will take it and put it in something called shift register, 10-bit shift register. So it will take your data and put it in that shift register, which you don't have access to, and enclose it by the start bit, which is always 0, and a stop bit, which is always 1. Okay. At that time, whenever your microcontroller reads this data and put it in the shift register, it will raise this flag to 1. And what is the importance of this? Whenever you see this flag 1, that means, or the transmission flag is 1, that means that the transmission buffer is empty, so you can write into it. Remember, if you write into it and the transmission flag was 0, that means there was data there, and if you write, you will overwrite it and you will lose your data. Okay? So you must wait until the transmission flag becomes 0 to write the new data. Okay. Step 3, it's also not your it is what the microcontroller will do afterwards. It will take this data and transmit them bit by bit into the transmission bin. Remember, each UART has 2 bins, one for transmission and one for receiving. For example, UART 0, which is our example here, uses B1.3 for the transmission. The 8 bits that you want to send will appear bit by bit on that bin 1.0. I mean, if you have some oscilloscope, you should see something like this in your oscilloscope from one bin. See, that's just the notes that I mentioned. First, you must check TX is a transmission flag register, TXIFG register. It's, by the way, called transmission TX interrupt flag register. So basically, now we have an idea that we can implement an interrupt based on that guy, okay, which is good. So you must check this guy, this bit, this flag, before writing a new data to the transmission buffer, because if it was 0, that means there is still data there that the microcontroller didn't handle yet. So this is an error, of course. And you must wait until this guy to become I'm sorry, 0 is this is what I said. Then it's not empty and you cannot write into the buffer. You know, to get rid of this dilemma or any overwrite problems, it's better to write your data into the transmission buffer based on interrupt. So you make interrupt service routine, and this interrupt service routine will be triggered whenever the TXIFG become 1, which means the buffer is empty. So now you will be sure that whenever I go to the interrupt service routine and write some data, this happens only when the transmission buffer is empty. So you will not have this problem of overwriting. Now the receive operation, okay? So it's similar to the transmit operation, but it's going in the other way around, because in transmission the programmer write the data first, but now it will receive. So now it's the opposite flow. So step 1 here starts whenever the hello. Sorry guys for this.
Welcome.
I don't know, the internet is very bad. It's really bad. Okay. Although I'm not just using the internet right now. So in the morning, my kids, they have also their online learning or online teaching or whatever. So yeah, it's understandable if I have some, interruption. But now I'm the only one that is using the internet. So I don't know. But anyways, so you guys can see my screen or yeah. Okay, we stopped at UART receiving process. Okay, I said it's really similar to the transmission process, but it's in the opposite way. Okay, so basically the receiving starts whenever you receive something on the receiving pin. Remember, there are 2 pins for each UART, one for transmission and one for receiving. For example, for UART 0, B1.3 is used for transmission, and the B1.2 is used for the receiving process. So whenever you receive a start bit, the transmission line or the wire was high all the time. Then at some point it becomes 0. Then there is an incoming byte or 8 bits. At that point, you will see that what's called receiving interrupt flag is 0. And that means you don't have yet any data in your receiving register or receiving buffer. Okay, so we have a transmission buffer and we have again a receiver or receiving buffer. Okay, and for UART 0, this is called UCA0 RX buffer for receiving buffer. So the receiving interrupt flag is 0, then there is no data yet to receive because the how can I say this? The receiving is not yet complete. Okay. The second step is when the receiver module or the UART receives the stop bit. At that time, it will write the 8 bits between the start and stop bits into your receiving buffer, RX buffer, and raises the flag here, the interrupt flag. Okay, and now it's the programmer responsibility to read that data. Okay, and this is really important because if you didn't read it, okay, and if there is still communication to happen or data to be received, then the microcontroller will overwrite your data. Okay, so you should all the time, empty this buffer or read it. Hello, guys. I'm sorry again. Okay, so we stopped at step 2. Let me share my screen again. So we stopped at step 2 in the receiving process. And as I said, whenever we receive the receiver module in the UART receives the stop, which is 1, then UART will write the data enclosed between the 8 bits enclosed between the start and stop bit into the receiving buffer. So it looks like this slide is really Guys, I'm gonna end this meeting, okay, and restart it because I don't know what's really happening.
Wait, can you, what'd you say?
He's gonna end the meeting and start it again. We'll just join back.
So I hope this time it will just, continue. Okay. So I think this slide is finished. So that's it. So let's go to another slide. Okay. So step 3. Now, after writing, after raising this flag, and the data is written from the shift register to the receiving buffer. Now it's your the programmer responsibility to read this data. Okay, and he must do so, because if he didn't read it, then there might be another data to arrive or to be received, and they will overwrite the old data in the receiving buffer. So that's very important. Okay, and when the programmer reads the 8 bits, okay, at that time the receiver interrupt flag will be 0, because the programmer reads the 8 bits, so the receiving buffer become empty again. Okay. This is the problem that I'm talking about, the responsibility of the programmer to read the data inside the receiving buffer, as long as there is a data there. Because if he didn't read the data and if he didn't read it on time, or in the correct time, another data may arrive, and whenever it's completed by the stop bit, the microcontroller will overwrite the old data with the new data that is recently received, and this is called overflow error. Overflow error. Okay, and luckily our microcontroller here have there is some question here. You guys has problems here.
No, we can hear you.
No, we hear you fine.
Okay. Because Jose is asking, I don't know. Okay, so luckily we have in our microcontroller, we have a register, another register. Okay, so we talk many registers until this point. Okay, it's called state register. Okay, so and this is so there is one state register in each UART, so you have 4 of them. So for example, for UART 0, we have this UCA0 state W register, and 1 bit in that register is called the overflow error bit. And if it's 1, that means you have an overflow error. You have some data that you didn't read on time. So it's good to check this upon receiving, of course, to check this bit if there is a problem or not. If you have some doubt about the receiving data that you are receiving, okay, it should be 0. If it's 0 all the time, that means there is no errors, overflow errors. There are also other kind of errors because you see, guys, it's 8-bit, okay, but we will not touch upon these errors because they are really rare to very, you know, rare to happen, okay. Now, how to configure and use our UART devices in our microcontroller. There are 3 main steps. The first one, again, like the timer, you have to populate some structure, some struct in your code with the required configuration. Okay, basically, one of these configuration is the baud rate. What kind of baud rate you want to use? Okay, either, for example, 9600 or, you know, 38600, you know, all such standard baud rates. Okay, of course there are other, you know, configurations as well, but most of them are just default, just copy and paste. The most important one are related to the baud rate. After that, remember that each UART needs 2 pins for the transmission and the receive. These 2 pins again will be used for the UART. Remember, each pin in the microcontroller can have multiple functionality. Okay, GPIO or UART or as a timer. Okay, so each one of those, as we said before, either, you know, the default functionality is a GPIO. Then you have a primary functionality, you have secondary functionality, you have tertiary functionality. Some pins have 4, you know, can work or can function with 4 different functions. Okay, for example, if you have a pin that can have that can work as a GPIO or part of some timer, for example, timer A1, and the part and also can work as a part of some UART, like for example UART 0, then this has a GPIO functionality. It has a primary functionality, which is a timer. It has a secondary functionality, which is UART. So you must define what kind of usage you want to use these pins. So as we say here, as we said before here, we have 4 UARTs, and each UART have 2 pins, and these pins should be configured as part of the UART module. You must do that. After you do the pin configuration, you finally write the configuration that you put in the struct to the required UART. You must do that. So you build the structure, you put all your configuration in it, but the module needs to know what kind of configuration. So you must, you know, make another command in your program to take that structure, which has the configurations, and send it to some particular module, like either UART 0 or UART 1, or whatever. Okay. One note here, as we will see after maybe 2 minutes, you will not write the baud rate directly in your structure, or your struct. You will write actually 3 numbers, which really have no, I have no idea what these numbers are representing, but they represent the baud rate that you have and the clock of the module or the microcontroller. Okay. So luckily there is a website, this website here, okay, that you can just go, it choose your baud rate, it choose your clock frequency. In our example, it will be 12 megahertz. So you just choose 12 megahertz in that drop down menu, and you click calculate, and it will pop for you 3 numbers or 4 numbers. Actually, we'll use only 3 of them, okay, which is the clock prescaler. This is the first one. Another parameter called the first mode register and second mode register. You just take these 3 numbers. These 3 numbers somehow are related to the baud rate and the clock frequency of of your if you UART and the microcontroller. Okay. Yeah. Another note or another important observation: how to write what is the proper way of writing data to the output. So if you want to transmit something, okay. So the rule says whenever you want to send, for example, 0, you send its ASCII code. You guys know what's meant by ASCII code?
What is meant by what?
ASCII, ASCII. This guy.
I'm not sure what that is.
So each symbol in your keyboard, okay, has a code. Okay. So for example, if you hit enter, this press will be represented by a code. This code is for hitting each keyword, each each button in your keyboard has its own how can I say this? Its own code.
Is it the binary that represents a symbol or
Yes, that's right.
that?
Yes,
Yeah,
that's
yeah.
right. Yeah, that's right. Okay, so let me go to any I'm sorry, any whatever. So ASCII code. So look, guys, if we open this, for example, look. So each, so for example, the letter B, for example, this letter B has its own code, okay, which is 70 in hexadecimal. Okay, so if you send 70 in hexadecimal, that means you are sending letter B. So you have two options in programming when you program, when you want to send something over the UART. You have two options. You either write its ASCII code. So here you are to transmit what is the module to transmit, and here is the message that you want to send, the byte that you want to send. So this is the actual command that you write to send something. So if you write it in that way with these double quotes, then the compiler will replace this with its ASCII code, and you will send really 0, and you will see 0. Another way is to write the ASCII code of 0. So if we go back to the HTML, so where is 0 here? Here is no, this is add. I'm sorry. Where is 0, 0, 0? Can you guys see 0?
It's hex
It's 48.
60.
Oh, wait.
Hex 60 or
That's
no hex 30. Sorry.
No.
Yeah, it's okay, this guy. Okay. So another option is to write 30. It's 30, guys. Okay. So you have two options. You either write, where is it? Yeah, you either write it like this, or you write it like this. Both are equivalent. So in the screen, we will see that on the screen, you will see in both cases 0, and that's good. But if you write it like this is the problem. This is not 0, because the compiler will think this is a decimal, this decimal representation of some symbol. So it will search for that symbol and represent it on your screen. We will see also that error together. Okay, so you have two options. You either write the hexadecimal of the hexadecimal symbol, the ASCII symbol of the byte, or the whatever the characters that you want to send, or you write it between these double quotes or even single quotes.
Professor.
Yes, Clark.
So if you send, in that spot right there, if you put, let's say, a variable or an array or something that you're going to transmit that data, will it retain that information, or will it convert those data within that information into ASCII?
So if you put here, I'm sorry.
If I put there, let's say like X.
A variable,
X,
right?
And it's 0. Yeah.
A variable?
Yeah. So if I put X in that spot,
Yeah.
and x is equal to 0, it's an integer.
No, you should write x equal to double quotes, 0 double quotes, or single
Okay.
quotes. Or
Got
x equal to 0x, it was 30, right? The next decimal of 0. It was
Yeah,
30,
so
I think.
instantiate, so instead of using integers, if you want to print something out, you have to use string.
Character.
Got it. Thank you.
Or use the hexadecimal, whatever you, if you, of course, you remember everything in the ASCII table, you are of course free to use the ASCII symbols. Okay.
I do not, unfortunately.
Okay. Good. So the last piece of cake here is, now we want to communicate something from our microcontroller to our PC. So we need to read that stuff that we are sending from the microcontroller to the PC. Okay. So to read that, we need some sort of software, that capable to interface us to what's coming on the USB. So one thing here before we continue, the connection between your PC and the kit is using USB. USB is a serial communication different from UART. Okay, so luckily we have on our our Launchpad kit, there is some hardware there, some chips that convert from UART protocol or TTL to USB protocol. So don't worry about that. Okay. Now we send something from our microcontroller. We send, for example, the letter A, and we need to read that on our PC. So we need a software. There are many of these softwares. Okay. One of them that I really found very convenient is called Serial Port Monitor. Okay, you just download. I will show you how to do that. You download it from that that link, and you install it very easy. It will give you 15 days 15 days free trial, and we have 15 days is very enough, very enough for us. Okay, so whenever you write something, so if you want to send something to your micro, you will put it here, then you click send. So so if you want to write something to your microcontroller, you put it here in that box, and click send. Okay, and whenever the microcontroller is sending something from you, it will appear here. So these are actually messages from the microcontroller. So you know what's really what is actually transmitted over your serial port or serial communication. Okay, guys. And finally, here is the program. Let's go over it together, but I will do that on the. You guys free to take screenshots, and I will send you the slides right now. Okay, so this program is basically, let me have, is basically do the following. We send something from the computer, from the PC, to UART 0. Okay, and of course this will be on bin 1.2. Then we take that stuff, we take that message, and we send it back to the computer. So we take it and send it back, echo. So if you receive A, you will send A. Okay, we will do a slightly different thing here, but this is the basic idea. So let's go over the program. So basically, you have first the structure that will have the configuration of your UART. Okay. First, you define the kind of clock source that you're gonna use, and we will use here the submaster clock. And in the main program, we will set the master clock to 12 megahertz. Okay. Then these three numbers are the numbers that we get from the website. So let's do that together. So we want to, I'm sorry, we want to use where is this website? Okay, let's do it from the presentation itself. So we want 9600 baud rate, and 12 megahertz. So we choose here 12, and then you hit calculate. And here are the three numbers that you see in the struct: 78, 2, and 0. And you must put them in order. Okay, you cannot miss the order. So yeah, so here are the three numbers that I'm telling you about. And these are, just a copy and paste. You don't just think about them. Okay, we only will use, this configuration, what kind of clock you are using, submaster clock or master clock or auxiliary clock, or the baud rate and the clock frequency. So here we are using 12 megahertz clock frequency, and the baud rate is 9600. Then we plug these three numbers here. So in the main program now, okay, this is, just put this as it is, but you can just ignore it. This watchdog timer, hold. Anyways, first you set your frequency to 12 megahertz, okay, and here is you are setting the functionality of the bits bin 1.2 and bin 1.3 as UART receive and transmission pins. If you revise or review the data sheet or the technical reference manual of your microcontroller, you'll find that this UART functionality for these two pins is the primary module functionality. GPIO is in primary, the secondary is in tertiary. Okay, so here I'm setting bin 2 and bin 3 as primary with their primary functionality. And why I am using the transmission and receiving? Because we will do both. We will receive something, then we will transmit it back. So we need to configure both bins. Of course, if you want to receive only, you just need to configure bin 1.2. If you want to transmit only, you just need to configure bin 1.3. You don't need to configure the other bin. Step 2 is to write the configuration, this configuration to the desired UART, which is UART 0. The name of UART 0 is that name. How could I know this? From the technical reference, from the driver lib library. So let's go to driver lib library to convince you more. So if you go to the driver lib library, where it is. Yeah. So here. What was this guy? UART init module. Yeah. So UART init module. First, it takes the module name, which is UART 0. This is the name of UART 0. This is the name of UART 1, 2, and 3. Okay. And then the name of the structure. So if you go back to our code here, here is the name of the structure. UART, but it needs actually not only the name, it needs the address of that structure. So we put this ampersand. Okay. We need to enable the UART module. Okay. So this is how to enable it. Then we need to enable the interrupt because we will do safe coding here or safe write and transmission and receiving. And we said that while we are explaining the UART transmission and receiving, we said that the transmission and receiving safely can be done using interrupt. So you are sure that you are not, messing with the transmission buffer or the receiving buffer. Okay, so we are enabling the UART interrupt. You shouldn't enable it in two steps. First, you enable the interrupt functionality in the UART module itself, UART hardware. Then, if you guys remember, you should also enable the interrupt functionality into the NVIC. If you guys remember the GPU interrupt, there was something called NVIC. NVIC is a module, the interrupt handler module. You know, it's a big hardware that is responsible for all the interrupts in your microcontroller. So you must enable it in both sides, in the hardware, in the UART module itself, and in the NVIC. It's another piece of hardware. And here are the two steps that do that for you. Then you interrupt you enable all the interrupts in your microcontroller, and you go into the sleep, you know, watch for interrupt, sleep. Okay, here is the interrupt service routine. Here is the, you know, the fun part. Okay, so I said that we will do something different, a little bit different than what's explained here. Okay, at least for that code. So first we receive, whenever we go here, that means that we received something. Okay, so whenever you receive something, then you go here and read that the receiving buffer. So to read from the receiving buffer or X buffer, you use this command here, UART receive data. Again, from where we know this is again in the driver lib. So if we go back, it's a little bit far above here. Yeah, UART receive data, UART receive, yeah, this guy. Okay. So you receive the data here, and what else? Yeah. Then after receiving the data, we want to transmit it back. Okay, so you must be sure that the transmission buffer is empty. Okay, and you remember, guys, it's a step that whenever we want to send something, we should be sure that the transmission buffer is empty. Okay, and the transmission buffer will be empty if the transmission interrupt flag register bit is 1. Whenever it's 0, that means it's not empty. So that's why here we are looping upon the second bit in that register, UCA0 interrupt flag register, which second bit is the transmission flag. Whenever it's 0, that means the transmission buffer is not empty. It has some data there that is not sent yet, and we must wait before writing new data to the transmission buffer. So whenever we break this loop, that means that guy become 1. We can write safely to the transmission buffer, and we write data to the transmission buffer using that command, UART transmission data. And here we will define what kind of module and the data that you want to send. The slight difference here between the highlight of this program and what I'm doing here is that I am all the time sending B, and I will show you why I'm doing that. So let's go now and check this code. So here is the code again. Let me change this to B again. Okay, so now the program is working. Okay, I am now grabbing the other. So this is the software that I'm telling you about, guys. Okay. So whenever you send something, you will see. So what's happening? What will happen now? When I write something. When I write something, it should be first. This program will echo this stuff here in that window, and we should see a breakpoint stop here. Then I will write, and I should see what's going back from the microcontroller again in that terminal window. So let me write, for example, Z. Okay, then I will click send. So I should restart. I'm serious. I should restart because. So let me restart this guy very quick. Okay, let's. The choice of the COM port is, so look guys, this is just, you shouldn't go deep into it, but for my computer you should check, for your computer you should check which port is connected to the UART. So to do that, you just write computer management here, and choose device manager, and port is COM LBT. So look here, UART is in COM5, okay? Just take it as it is. So this is how to know which COM to use. So in my case, I should use COM5, okay? And I should click open or, session, new session, COM5. You choose this all, start monitoring, yeah, and be sure that is 9600. Then we're gonna see now, a real fun. So this program is running now, but I didn't send anything yet. So I will, for example, write A, send. So first it will echo what I'm sending into this terminal. So I just sending, nothing received yet. But since I put here a breakpoint, and now the transmission, the receiving buffer is full, because the microcontroller, the UART is the microcontroller has received something. Now it will go to the interrupt service routine. And you see, guys, here we are in the interrupt service routine. So let's go forward step by step. So let's check this guy. Receive the value. Receive the value is A. Look, the value of this variable is A, which I was sending in here, right? So we are in the correct. So we received the correct message. Okay. Now. I will of course check on the transmission buffer. It's empty. Good. Now I will write back B. So the received data is, just you can call it whatever, but yeah, this variable. Now I will write back B. So let's see what's gonna happen in here. Look, we have B. It's really fun. So you put, for example, Z. Let me shrink this a little bit. Let us write Z. Send. Here is Z. You guys see Z. And so yeah, we didn't, yeah. So there is a problem here. Good. So let's check the value of that guy. It should be Z. That's right, it's Z. Then I just continue. We should write B here again. Okay, let's write, for example, S. Send. Again, we are here. Continue. Again, B. Okay, so it's really nice. Let's write, for example, another weird character. So let's go to the website here. Guys, when you hit enter, you go to another line. We will do that now. So where is that? Where is that? In yeah, new line. New line is hexadecimal A. Or yeah, hexadecimal A. So right, I will or 10. Okay. So let me write 10 there. 10 as decimal. So instead of B, I will write 10. But 10 as it is. You know, this is ASCII code of this new line stuff. So let us now recompile this guy. Okay, let's run it. It doesn't receive anything, so we didn't touch this the interrupt service routine yet. Now let's send, for example, if. What I'm gonna see now, I'm gonna see if here. Then whenever I go to that interrupt service routine, I will write carriage return, which is just like hitting enter. So you will go to another, another line. We will see that. So let's hit send now. We are here. Let's check that we are reading really if. It's if, that's good. Then we do that. We didn't see anything. Actually, there is something. So let me show you. If I write, for example, now V, look now, V on another line. Okay. And, let us also, we have also another new line, carriage return or hitting enter. So if I write, for example, C, I will see it on another line, and so on. Okay, it's really fun. Okay, guys, so have fun. I am with you. You have, half an hour or something. That's fine. Take your time. There will be, many problems especially with that guy. Okay, when you download it and start it. Okay, and knowing what kind of board or what kind of COM board you're gonna use. So I'm expecting that. So I will be here to help you. So take your time. Yes, Clark.
Is that that's a different software, right? That one that you use to input things into the serial port monitor?
It is the same one, serial port monitor.
Yeah, is that a different software we have to download?
Yeah. You have to download. This is the one that in the slide. I will send the slide now for you. I'm very sorry for this.
Yeah.
But it's called the serial port monitor. You just search it, it will appear to you. But I will send it now the. Okay, guys. So just start writing. I will send now the slides for you. So I sent it. I sent the slides on Canvas. You can just check now. Okay. So in the slide you will have this. This link to this. Let me share my screen again. You'll have this link for that's, and also I will open for you the the yeah. You can just download it. Okay, it will give you 15 days trial. Okay, guys, I will just go for 5 minutes and come back. Just 5 minutes, okay?